Good morning, everyone. Welcome back to Doc Chilma online tutorial. The topic I will be discussing for today's tutorial is all about limits and introduction to calculus. This is actually the continuation of the topic discussed to you last time, which was the basic concepts on limits. Determine whether limits of functions exist. Use properties of limits and direct substitution to evaluate limits. These are just the two objectives of today's tutorial. Let's have first a simple recall on the definition of limit. If f of x becomes arbitrarily close to a unique number n as x approaches c from either side, then the limit of f of x as x approaches c is n. This is written as the limit f of x as x approaches c is equal to n. Now let's have first an illustrative example on the simple recall of estimating a limit numerically. Use a table to estimate numerically the limit of 4x minus 3 as x approaches 2. Let f of x be equal to 4x minus 3. Then, construct a table that shows values of f of x for two sets of x values. One set that approaches 2 from the left and one that approaches 2 from the right. F of x is equal to 4x minus 3 as x approaches 2. Consider the table below between x and f of x. From the left of 2, from the values of x that ranges from 1.0 to 1.9, f of x here comes closer to 5, since 4.6 here is approximately equal to 5. Now, from the right of 2, from the values of x ranges from 3 to 2.1, as you can see here, f of x comes closer to 5, since 5.4 is approximately equal to 5. So from the table, it appears that the closer x gets to 2, the closer f of x gets to 5. So we can actually estimate the limit to be 5. Figure 1 illustrates the conclusion. Graph of 4x minus 3. F of x is equal to 4x minus 3. The limit of 4x minus 3 as x approaches 2 is simply equal to 5. So as you can see here in the given graph, okay, so here is the point where x is equal to 2. It gives f of x to be equal to 5. Limits that fail to exist. So in this next slide, we will examine some functions for which limits do not exist. Let's have an example, comparing left and right behavior. Show that the limit does not exist. The limit of the absolute value of x over x as x approaches 0. If we take positive values of the absolute value of x over x, that is just equal to 1 for x is greater than 0. And if we take negative values of the absolute value of x over x, which is equal to negative 1, or x is less than 0. Consider the graph of f of x, which is equal to the absolute value of x over x. Okay, so we construct a Partition plane here. Okay, so as you can see, we have the graph of f of x equals 1 and the graph of f of x equals negative 1. So as you can see, the graph of f of x, which is equal to the absolute value of x over x, splits, okay, into two graphs. Okay, so take note of that. So this means that no matter how close x gets to 0, there will be both positive and negative x values that yield f of x equals 1 and f of x equals negative 1. So there is a discontinuity in the graph of the absolute value of x over x. So this implies that the limit does not exist. Following are the three most common types of behavior associated with the non-existence of a limit. Conditions under which limits do not exist. The limit of f of x as x approaches c does not exist when any of the following conditions are true. F of x approaches a different number from the right side of c than it approaches from the left side of c. F of x increases or decreases without bound as x approaches c. Then f of x oscillates between two fixed values as x approaches c. So these are just the three conditions under which limits do not exist. So take note of that. Then we have the different properties of limits and Erect substitution. You have seen that sometimes the limit of f of x as x approaches c is simply f of c, as shown in the illustrative example number 1. In such cases, the limit can be evaluated by what we call a direct substitution. That is, the limit f of x as x approaches c is just equal to f of c. Substitute c for x. There are many well-behaved functions such as polynomial functions and rational functions with non-zero denominators that have this property. The following list includes some basic limits. Let b and c be real numbers and let n be a positive integer. The limit of b as x approaches c is equal to b. So this is simply the limit of a constant function. The limit of x as x approaches c is equal to c. Simply this is the limit of the identity function. Limit of x raised to n as x approaches c is equal to c raised to n. The limit of a power function. Then we have the limit of the nth root of x as x approaches c is equal to the nth root of c, for n even and c is greater than 0. The limit of a radical function. This list can also include trigonometric functions. For instance, we have here the limit of cosine x as x approaches pi. Take note, cosine of pi is simply equal to negative 1. And the limit of sine x as x approaches pi over 2, take note that sine pi over 2 is also equal to 1. So take note of that. Sine pi over 2 or sine 90 equals 1. And cosine of pi is the same as cosine of 180, which is simply equal to negative 1. By combining the basic limits with the following operations, you can find limits for a wide variety of functions. Okay, so we have here 5 properties of limits. Let B and C be real numbers, let N be a positive integer, and let F and G be functions with the following limits. The limit of f of x as x approaches c is equal to L, and the limit g of x as x approaches c is equal to k. Then we have here the scalar multiple, the limit of b times f of x as x approaches c is equal to b times L. Then we have the sum or difference, the limit of f of x plus and minus g of x as x approaches c is also equal to L plus and minus k. And we have the product properties of limit, the limit of f of x times g of x as x approaches c is equal to L times k. And we have the quotient properties of limit, the limit of f of x over g of x as x approaches c is simply equal to L over k. Take note, k must not be equal to 0. Otherwise, this must be undefined. Then we have the power properties of limits, the limit of f of x quantity raised to n as x approaches c is simply equal to L raised to n. Now, let's consider example number 3. Find each limit. Limit 2x as x approaches negative 1. So by direct substitution, we have 2 times negative 1, that is simply equal to negative 2. In this case, property 1 is illustrated. The limit of cosine x over x as x approaches pi over 2 is just equal to cosine pi over 2 over pi over 2, which is simply equal to 0. Take note, 0 over pi over 2 is 0. In this case, property 4 is illustrated. Then we have the limit of x times sine x as x approaches 3 pi over 2. So we have limit of x times the limit of sine x, so which is just equal to 3 pi over 2 times negative 1. Simplifying further, we have negative 3 pi over 2. So take note, this is simply negative 3 pi over 2. Property 3 is illustrated. Then let's have example letter D. The limit of x squared as x approaches 4 is the same as the limit of the quantity x as x approaches 4. The limit of the quantity x squared. Okay? So that's 16. Since 4 squared is equal to 16. This time, property 5 is illustrated. Then we have here the limit of x minus 5 quantity squared as x approaches to 8. Which is just equal to the limit of x minus the limit of 5 quantity squared as x approaches 8. So we have 8 minus 5 quantity squared or 3 squared, or that is simply equal to 9. This time, property 2 and property 5 is illustrated. Example number 3 shows algebraic solutions. To verify the limit in example 3D numerically, for instance, create a table that shows values of x squared for 2 sets of x values. One set that approaches 4 from the left and one that approaches 4 from the right. So as shown below. So consider the table of values between x and x squared. From the left of 4, for the values of x ranges from 3.9 to 3.999999. Okay? X squared here comes closer to 16. Since 15.9920 is approximately equal to 16. Now, from the right of 4, from the values of x ranges from 4.1 to 4.001, as you can see, x squared comes closer to 16, since 16.008 is approximately equal to 16. From the table, you can see that the limit as x approaches 4 is 16. To verify the limit graphically, we sketch the graph of y equals x squared. From the graph shown in figure 2, you can determine that the limit as x approaches 4 is 16. So as you can see here, so if x is 4, we have here f of x is 16. Okay? I hope you did understand the limits and introduction to calculus. Okay? And I want to thank you once again for watching and stand by for my next tutorial. Again, may God bless us all.